Hey guys, hope you are all doing fine. In this video, we will look at projected gradient method and then look at the properties of the gradient map. Having looked at several examples of the projection operation, we are now ready to look at the projected gradient method. Recall that we were considering the problem min over x in calligraphic x, f of x, for a smooth function f. The updates of the projected gradient method take the form xt plus 1 is equal to projection onto calligraphic x, xt minus eta gradient of f of xt, where the step size eta is greater than 0. So suppose that this is my set calligraphic x. Then we are first going in the direction of the steepest descent by disregarding the constraint calligraphic x. Then we are projecting the result back onto calligraphic x. In other words, we are finding the point that we would have ended up had there been no constraint, and then finding the nearest point within calligraphic x to that unconstrained point. Another way of writing the update is to expand the projection part and write it as xt plus 1 is equal to r min over x in calligraphic x, norm square of x minus xt minus eta gradient f of xt. Now we can multiply the objective by a scalar and add constant terms to it without changing the optimum, so we can write the right hand side as r min over x in calligraphic x 1 by 2 eta norm square of x minus xt minus eta gradient f of xt plus f of xt minus eta by 2 norm square of gradient f of xt. So the reason we have added these terms and scaled is that then we can expand and write the right hand side as r min over x in calligraphic x f of xt plus inner product of gradient f of xt x minus xt plus 1 by 2 eta x minus xt norm square. So this is another way of looking at the projected gradient descent. We are constructing a quadratic approximation of f at xt and then minimizing it while being constrained to calligraphic x. In other words, the problem of minimizing f over calligraphic x has now been reduced into a series of problems, one to be solved at every iteration, and involves minimizing a quadratic function over calligraphic x. This interpretation is very interesting because it allows us to develop other variants of the projected gradient descent. For example, we will use it to develop the proximal gradient descent and mirror descent. We can have a look at the contour plots of the problem in order to get an intuition. Consider a function in R2 whose minimum occurs at 4, 4. However, suppose that we need to minimize f over the constraint calligraphic x, which in this case is the norm ball. So the constraint region does not include the point 4, 4, and therefore the optimum will lie on the boundary of calligraphic x. Suppose we are starting at the point marked by the triangle. Now let us take a step of the projected gradient descent. The black arrow shows the direction of the steepest descent. As you can see, if we let x go in that direction, we'll end up outside calligraphic x. However, if we apply the projection operation, it brings us back to the point within calligraphic x. So we end up proceeding along the direction of the red arrow. And we continue in the same way for other iterations as well. So each time the steepest descent takes us outside the calligraphic x, and the projection operation brings us back inside calligraphic x. In the end, we end up with a sequence of steps which are along the boundary of calligraphic x and ultimately with the optimal point that is also on the boundary. Let us take another look at the optimality conditions. Recall that for constraint problems, gradient f of x star is not necessarily 0. We have already seen the optimality condition that the inner product of gradient f of x star, z minus x star is greater than or equal to 0 for all z in calligraphic x. Another optimality condition that is inspired from the update equation is that x star is equal to projection onto calligraphic x star minus eta gradient f of x star. This is basically the fixed point of the updates provided. To see that this is in fact the optimality condition, suppose that x star satisfies this. Let us recall the angle property of the projection operator, which was that inner product of x minus projection onto calligraphic x of x comma z minus projection onto calligraphic x of x is less than equal to 0 for all z in calligraphic x. In this equation, replace x with x star minus eta gradient f of x star. And then projection of x onto calligraphic x can be replaced with x star. Substituting these into the angle property, we get that gradient f of x star z minus x star is greater than or equal to 0 for all z in calligraphic x. So this is exactly the optimality condition written above. An intuitive way to proceed with the analysis is to utilize the idea of gradient mapping. The idea is that we will write down projected gradient descent such that it looks similar to gradient descent. That is, xt plus 1 is equal to xt minus eta g eta of xt, where the term g eta of xt is defined as 1 by eta x minus projection onto calligraphic x minus eta gradient f of x. This is called the gradient mapping. Of course, if calligraphic x was the entire space V, then the gradient mapping would be the gradient itself. In general, however, we can see that the gradient mapping has several properties that are similar to those of gradient. That will allow us to analyze projected gradient descent by following a similar proof outline as the gradient descent. So let us look at the various properties of gradient mapping. The first thing is that gradient mapping is 0 at x star. That is, g eta of x star is equal to 0. This follows by writing out the definition of g eta of x star, which is that 1 by eta x star minus projection onto calligraphic x star minus eta gradient f of x star. So which is 0 from the optimality condition that we just now saw. Compare this to the gradient descent, where the corresponding property was that the gradient vanishes. Instead, here we have that g eta of x star vanishes. Interestingly, it turns out that PGD is also using a descent direction. Recall that for unconstrained problems, minus gradient f of x was a descent direction. Here it turns out that negative of g eta x is also a descent direction at x. To see this, recall the angle property x minus px of x inner product with z minus px of x less than or equal to 0 for z in calligraphic x. Replace x with x minus eta gradient f of x. Then we can see that projection onto calligraphic x minus eta gradient f of x can be written as x minus eta g eta of x. So let me copy the rest of the terms. So we have this inequality for all z in calligraphic x. Now we can replace z with x because we are assuming that x is already in calligraphic x. So as to obtain this inequality, cancelling out all the common terms and then rearranging, we obtain that inner product of gradient f of x with minus eta g eta of x is less than or equal to minus eta norm square of g eta of x, which is less than or equal to 0. So in other words, which is saying that the negative g eta of x is a descent direction, since it makes a obtuse angle with gradient f of x. Another way of writing this property, if we cancel eta, is that gradient f of x inner product with g eta of x is greater than or equal to norm square of g eta of x. Or equivalently, g eta of xt minus gradient f of xt inner product with g eta of xt is less than or equal to 0. So these two properties will also be useful later. So to summarize, we have seen that the gradient mapping is 0 at the optimum, and at all other points the negative gradient map is actually a descent direction. Let us look at some properties of the norm of the gradient map. We have the following monotonicity property, which says that if eta 1 is greater than or equal to eta 2, then g eta 1 of x norm is less than or equal to norm of g eta 2 of x, and eta 1 times norm of g eta 1 of x is greater than or equal to eta 2 times norm of g eta 2 of x. So in other words, we are saying that norm of g eta is a decreasing function of eta. However, eta times the norm of g eta is an increasing function of eta. So let us look at the proof of these properties. We begin again with the angle property, which is saying that x minus px of x inner product with u minus px of x is less than equal to 0. And now we replace x with x minus eta 1 of gradient f of x. Also we replace u with px of x minus eta 2 gradient f of x. So as to get the following expression, x minus eta 1 gradient f of x minus the projection of the same thing, inner product with projection of x minus eta 2 gradient of f of x minus projection of x minus eta 1 gradient f of x. This whole thing is less than equal to 0. Now recall the definition of the gradient map and substitute px of x minus eta 1 gradient f of x as x minus eta 1 g eta 1 of x, and px of x minus eta 2 gradient f of x as x minus eta 2 g eta 2 of x, and likewise the third term in the same way. Substituting all of these, we get eta 1 times inner product of minus gradient f of x plus g eta 1 of x with eta 1 g eta 1 of x minus eta 2 g eta 2 of x. So this whole thing is less than equal to 0. We have been able to obtain this inequality for arbitrary eta 1 and eta 2. And therefore in this inequality we can always interchange eta 1 and eta 2. So as to get eta 2 times inner product of minus gradient f of x plus g eta 2 of x, comma eta 2 g eta 2 of x minus eta 1 g eta 1 of x less than equal to 0. So the reason we have interchanged is that now if we add them after dropping these factors eta 1 and eta 2, then upon adding, the minus gradient f of x terms will cancel. And what we will get is inner product of g eta 1 of x minus g eta 2 of x, comma, eta 1 g eta 1 of x minus eta 2 g eta 2 of x is less than equal to 0. So now let us expand this so as to get eta 1 norm square of g eta 1 of x plus eta 2 norm square of g eta 2 of x less than equal to eta 1 plus eta 2 inner product of g eta 1 x, comma, g eta 2 of x. And then we will use the Cauchy-Schwarz inequality on the last term so as to get that it is less than equal to eta 1 plus eta 2 norm of g eta 1 of x times norm of g eta 2 of x. So now what we can do is bring it over to the left side and then combine it back so as to get that the product of norm of g eta 1 of x minus norm of g eta 2 of x with eta 1 norm of g eta 1 of x minus eta 2 norm of g eta 2 of x is less than equal to 0. So finally we have this product of two numbers which is negative, which means that one of them has to be negative and one of them has to be positive. It is already given that eta 1 is larger than eta 2. So under that condition you can verify that the only possibility is that the first term is negative and the second term is positive. That is, norm of g eta 1 of x is less than equal to norm of g eta 2 of x, and eta 1 norm of g eta 1 of x is greater than equal to eta 2 norm of g eta 2 of x. So for the case when eta 1 is greater than eta 2. So in summary, we have proved that norm of g eta is a decreasing function of eta, but eta times norm of g eta is an increasing function of eta. Next we'll show the Lipschitz continuity of the gradient map. Recall that gradient f of x is Lipschitz continuous with parameter L. It turns out that the gradient map is Lipschitz continuous with parameter L plus 2 by eta. The proof uses non-expansiveness of the projection operation. Let us derive it. By the definition of g eta, we have that norm of g eta of x minus g eta of y is equal to 1 by eta norm of x minus px of x minus eta gradient f of x minus y plus px of y minus eta gradient f of y. Now let us use the triangle inequality to get the x minus y term separate from the projection term, so as to bound the right hand side with 1 by eta norm of x minus y plus norm of projection of x minus eta gradient f of x minus projection of y minus eta gradient f of y. Next, we use the non-expansiveness of the projection operation, which yields that the left hand side is less than equal to 1 by eta norm of x minus y plus norm of x minus eta gradient f of x minus y plus eta gradient f of y. Now again use the triangle inequality to separate out the x minus y term. So we get the right hand side as less than equal to 2 by eta norm of x minus y plus gradient f of x minus gradient f of y norm. Now finally, from the Lipschitz continuity of the gradient f of x, we have that the second term is bounded by L times x minus y norm. Therefore the whole thing is bounded by 2 by eta plus L norm of x minus y. Finally, we take a look at the monotonicity property. It says that if f is smooth and convex and eta is less than 2 by L, then it holds that g eta of px of x minus eta gradient f of x norm is less than equal to the norm of g eta of x. So another way of writing the same inequality, recalling the definition of g eta of x, is that norm of g eta of x minus eta g eta of x is less than equal to norm of g eta of x. So suppose that we are at x, then the norm of the gradient map evaluates to norm of g eta of x, which is on the right. Then if we take one step of PGD, then we get x minus eta g eta of x. And then if we take the norm of that quantity with the gradient map, we would get the left hand side, which is the result says is less than equal to the right hand side. So in other words, what we are saying is that the application of PGD update results in the norm of the gradient map to decrease for a smooth and convex function for eta less than 2 by L. In other words, the sequence g eta of xt norm is non-increasing with t. To see the proof, let us denote x plus as the projection of x minus eta gradient f of x onto calligraphic x. Then from this definition, we have that the norm of g eta of x plus, which is the left hand side in the original inequality, is equal to 1 by eta norm of x plus minus projection of x plus minus eta gradient f of x plus. Now let us substitute the definition of x plus here so as to get 1 by eta projection of x minus eta gradient f of x minus projection of x plus minus eta gradient f of x plus. So at this point we can use the non-expansiveness of the projection operation so as to get 1 by eta norm of x minus x plus minus eta gradient of f of x plus eta gradient of f of x plus. Now at this point we could use the triangle inequality, but then we would not get the required result. So actually we need a stronger result so as to get the required bound. So let us keep this inequality for now and look at the smoothness of function f. Recall the property for L smooth and convex functions, which is that the norm square of gradient f of x minus gradient f of y is less than equal to L times the inner product of gradient f of x minus gradient f of y comma x minus y. So let us see what this property implies. Let us denote u is equal to gradient f of x minus gradient f of y and v is equal to x minus y. So in that case, this property is actually saying that norm square of u is less than equal to L times inner product of u comma v. Therefore the term that we had obtained so far can be written in terms of u and v as eta u minus v norm square, and expanding it, it is equal to eta square norm square of u plus v norm square of v minus 2 eta inner product of u comma v. So here the last term can be bounded from the smoothness condition we have just derived, and therefore we will get the whole thing is less than equal to eta by L times eta L minus 2 norm square of u plus norm square of v. So now we just assumed that eta was less than 2 by L. In other words, eta L was less than 2, and therefore the first term here is negative and can be dropped. So this whole thing is less than equal to norm square of v. We have therefore concluded that the term we had is less than equal to 1 by eta norm of x minus x plus, which is nothing but norm of g eta of x. So in summary, we have seen that the gradient mapping, which is defined as g eta of x equal to 1 by eta x minus px of x minus eta gradient f of x, serves as a useful proxy for gradient f of x and satisfies the following properties. So let me summarize all the properties. First, we have the stationarity condition, which is that g eta of x star is equal to 0. Then we have the descent property, which is that minus g eta of x is a descent direction, or inner product of gradient f of x comma g eta of x is greater than equal to norm square of g eta of x. Then we had that norm of g eta of x is a decreasing function of eta, while eta times norm of g eta of x is an increasing function of eta. Then we had that g eta of x is Lipschitz continuous with parameter 2 by eta plus L. And finally, if f is convex as well as smooth, then the gradient norm is monotonic across the iterations of PGD for eta less than 2 by L, norm of g eta of x minus eta g eta of x less than equal to norm of g eta of x. So you don't need to remember these properties, but this is just a handy reference for you and especially useful when obtaining results. So that is all for this video. In the next video, we will obtain the Oracle complexity bounds for PGD for smooth functions.